Now for the second part of the problem 2 of homework 4, I asked you to compute the part of the weak form considering some arbitrary variation that I gave you. But consider just any arbitrary variation delta u that could be applied either to the reference configuration or to the deformed configuration. And we have the null values. Similar to any of the other fields, any of the other vector fields that we have, you can always compute delta u as the sum of the shape functions. I'm going to use the b here. Sum of shape functions b times the nodal values. Actually, I should still use a. But it doesn't matter, really. This is a dummy index, so it doesn't matter what you choose. So that will be the interpolation, again, for any xi. I could have the shape functions, which are in terms of xi, to interpolate the variation anywhere inside of the quadrilateral. And then this is the same, so this delta u is the same no matter if I do it for the so this will be interpolation in the parent domain, and like I say, you can always associate this with the reference or the deformed x's. And then the question is, what do I need to compute for the weak form? I need to compute either this delta d, which is the symmetric velocity gradient, or delta e. So we can do either one. Let's just start with the delta d, which is the one in the homework. So delta d is the symmetric velocity gradient, so that will be 1/2 of gradient with respect to little x of this virtual variation, of this virtual displacement, or this variation, plus gradient with respect to x of delta u transpose. With how do you compute the gradient? This gradient, well, this is just sum of the nodal values, delta u a, dyadic product with the gradient of the shape function with respect to little x. And these are the nodal values, and these you can calculate based on what I showed you above. So you can always compute the gradients of the shape functions with respect to little x or capital X. So you should have everything. So you can compute that, and that's how you can compute the variation, this variation d, the variation of the symmetric velocity gradient for any point in here. Similarly, what about delta E? So delta E is F transpose gradient with respect to the capital X of delta U plus gradient with respect to the capital X of delta U transpose F. 1/2 of this. And so you have F here, F you calculated before, and then here, this I didn't ask you to compute in the homework. But this gradient will be the same as before. So this gradient would be the gradient of this delta UA dyadic, but in this case dyadic with the gradient of the shape functions with respect to capital X. And then here you also need the deformation gradient F to compute delta E. So that's how you would compute delta E for any point in the parent domain and the corresponding point in either the reference configuration or the deformed configuration. So, and that's given that you know these values, given that you know the values at the nodes of the variation, right? Which is what I asked you to do in the homework problem too. And, so you have F here, F you calculated before, and then here, this I didn't ask you to compute in the homework. But, this is what I asked you to do in the homework problem too. And, so you have F here, F you calculated before, and then here, this I didn't ask you to compute in the homework. Right, which is what I asked you to do in the homework problem too. the last step is, because you can calculate this easily, then the question is, you can compute, in that case, easily compute the integrals, for example, over the, let me denote it, well, I should denote it like B0E. B0E, that's the reference. So the second compute at Kirchhoff stress, which again, because you have the deformation gradient F, you can compute this second compute at Kirchhoff stress, double contracted with this delta E over the integral. So compute this. This will be essentially the sum over the integration points of the weight of the integration point times the determinant of the Jacobian of the isoparametric map. This is determinant times S evaluated at the corresponding, basically F at the corresponding integration point, right? Double contracted with delta E. Also at the same, you can see that the delta E also depends on F and on having these variations, which are both interpolated based on, so this depends on both F, which depends on the integration point, and also this delta U, which also might change from integration point to integration point. But you have them, right? You have the formula for how to calculate delta U, you have the formula for how to calculate the gradient of this virtual displacement with respect to either the lowercase x or capital case X for any value of xi. So therefore, if you can do it for any value of xi, because your shape functions are in terms of the xi, you can do it for the integration points. So that's how you can compute that integral. Similarly, same thing as before, you need, if you want to compute the integral sigma double contracted with delta D, again, this can be sum over the integration points of this times the Jacobian, the determinant of this Jacobian, times sigma, which depends on having F computed at the integration points, double contracted with this delta D, which this one doesn't depend on D, this directly depends on delta U. Integration points. So that's how you would compute either one of these integrals, and then however many integration points you need. But hopefully this clarifies second part of problem 2. I didn't ask you to actually compute the integrals, but I did it in the solution. So I actually computed the integrals. And there was one thing, maybe I'll explain that when I make the video for the Python notebook of the homework in a sec. But this integral actually for the problem that I defined in the homework, this one is actually 0 if you adjust a little bit the variation that I gave you. Yeah, but I'll talk about that in another video. But hopefully this clarifies, if you had some arbitrary variations, delta U, at the notes, how you would compute then these integrals. So I'll stop right here, and then I'll do the last video that I want to do with derivations is basically the residual. So